Testing, testing. All right. Let me have your attention, please. Yeah. So the due date of the lab 1 has been passed. So like for the submissions on the GitLab recorded before like the due date, you will get the 100% of the credits. So like I will run the grader over the weekend. So like starting up the next weekend, you will see the earned points in Canvas in the like the lab 1 section. But you can make a late submission. So like the submissions are opened until the last day of the semester. So like if you submit the late assignment before December 9th, then I will assign like the 50% points of the credit for that. And please start the lab 2 as soon as possible. So like it has around the 2 weeks of the due date. And any questions for the lab 1 submission? I believe that most of students were struggling with the stack frame, and then like once they understood how EBP works, then the lab 1 was not that difficult. But I believe like you guys struggled a lot with some tools in the environment, and then like after like getting familiarized with those tools, your coding and then debugging will be much faster for lab 2 and on. And we will have quiz 1 on next Tuesday. And then I will announce about more detail about the quiz at the end of this lecture. And then we will have the lecture for the quiz prep on Thursday. But on Thursday, there will not be in-person class. So I will record a video, then they release that to you for the quiz prep. The main reason is like you can watch the video while solving the quiz. So like that will be very helpful for the quiz. And then like one special style of the CS 444, 544 is there's no time limit on quiz. And then you will have up to 3 trials. And then the quiz is open for open material. So don't search on the internet, but you can refer to any materials, slides, tutorial videos, or even quiz prep videos. Yeah, these are all yours. And then quiz will be open for 2 days. So like I believe like everybody will have like plenty of time. So there will be practically no time limit for the trial. So I will set it as like more than 10 hours. So like please take enough time to get the best score that you can get. So the reason why I have quiz in this style is that like it's very important to know certain things before move on to the next step. So even if you didn't study or like they don't know the detailed concepts from the lecture, then during the quiz time, that's the time that you can study about the contents, and then like even if you get a wrong answer, then you can get the which answer is wrong, and then you can correct that in the subsequent trial. So I believe like that after finishing quizzes with the perfect score, then you will realize that you know something than before. And then like I will take some questions about the quiz at the end of this lecture. So I will have a few more slides for the quiz. And then before getting into the topic for today, let's do a little bit of a recap about like what we have learned in the last week. So in the last lecture, we learned about the setting the memory permissions in the page table and page directory entries. And then they do have present, writable, and user flag. And then present flag means that if that is 1, then the page is existing. So it has been allocated. And then if that is 0, then that's an empty entry. And then for writable, if that is 1, then we can write on the memory. So CPU will catch and then verify the permission on every memory translation. So no matter at which time the CPU tries to write on the memory, then from the address, then corresponding entry, the flags, we can verify that the target memory is writable or not. And then if that flag is 0, then CPU will block any kind of writing. and then it will generate the segmentation fault. And then the last one is like the PTU. And then we do not use user level ring 3 until we get into lab 3. So like the up to lab 2, you will just playing around the ring 0. So you will not see the real power of the PTU flag. But we use this to isolate a certain part of the memory from the application program. So like if we set like a PTU as a 0 for the OS kernel part of the memory, then application, for example, Google Chrome or some other application running on your laptop cannot touch anything owned by the kernel by setting the PTU as a 0. And another important thing is that the CPU will check both entries. So the real permission will be the result of the intersection of the flags in the page directory entry and page table entries. So for this address, with these kind of the permission set up, so if we take the intersection, then only the PTP will be remaining. So the address is a valid address because both has a PTP, but it's inaccessible by ring 3. So it's kernel only because PTE misses a PTU flag. And then it's not writable because PTE misses PTW. So the easy way to get the permission is that like just taking the set intersection of the flags, and then you can identify what kind of permission it will have. Or you can also mechanically act like a CPU. So you can check PTE first. So inaccessible by user because there's no PTU. And then after that, if it is a writable, so writable and kernel from the kernel, but at PTE, you will see that there's no PTW set. So you will realize that the CPU should block this access. So the important takeaway is that the virtual address, when translating, CPU translates the address, it will check a PTE first and then PTE. So the general practice is that we will set more permissive permission. For example, allow everything, for example, for page directory entry, but we should set the strict or tighter permission for the page table entry. This is because if we miss some of the flag in the page directory entry, then every single page table entries under that linked by that page directory entry, that will be all invalid. And then there could be some of the conflicting setup for the permission setup for kernel and user. And in such a case, we can work around by assigning a new address for it. So the example of those is that, so suppose we want to set up the kernel readable, writable, user readable. So that's okay, because for kernel readable, writable, then for the user, what we said is the assign a virtual address, and then just the read-only access to give user the read-only access to the address. And then at the same time, we can map the same physical address to a different virtual address, but we can allow kernel reader write, but no user access at all. We can also set kernel read-only, user read writable, readable writable memory, and the method is the same. For the same physical address, we will set the different virtual address, and then we can have a completely independent flags for that. And then we can also assign not accessible by kernel, but accessible by the user, just having the mapping for the user, not for the kernel. But the problem of this kind of mapping is that because kernel, if they access the user address, then they will have the same permission with the user. Any questions for the recap? So the important thing is that on quiz, there will be some questions about the address translation and permission flags. So please walk through these slides well before taking the quiz. And the topic for today is managing physical and virtual memory in JOS. So I would like to visualize some of the things that you can understand better for Lab 2. So we need to create a virtual memory space in Lab 2 for JOS. And we know that the CPU, the CR3 register inside the CPU will point to the page directory, and the page directory will manage the entire virtual memory space. And then you can think it as per each process, we will have a separate page directory to give a separate independent virtual memory space to them. And how it works is that, suppose the target page directory is at the physical address 0x153000. So the reason why we have a last 3 digit as a 0 is that all the page table directory, they will be page aligned. And then if the CR3 correctly points to a page directory at here, then graphically, it's something like a CR3 is pointing to the page directory. And then under this page directory, inside of this page directory, because it's a 4 kilobyte, and then each entry will be 32-bit, 4 byte. So we will have a 2 to the 10, 1024 entries available. And each entry in page directory will point to the page tables. So there will be a lot of page tables like this. And then like each page table entry will point to the physical page number that falls into like a 4 kilobyte block. So you can regard each block of the page table entry will manage and allow the translation for the 4 kilobyte page. And then how many entries available in the page table. So that's also the same 1024. So what that means is that, so suppose there is a 1 entry in page directory. Suppose you set this page directory entry to have a PTEP, the present flag as 0. That means you are invalidating this specific entry. Then it will block access to all of the page table entries. And then for the size of the memory, we can calculate that. So each entry will manage 4 kilobyte. And then in the page table, we have 1024 entries. So 4 kilobyte multiplied by 1024, that's exactly 4 megabyte. So each page directory entry will manage the permissions for 4 megabyte. And then let me illustrate how you can assign a virtual address to a physical address. Suppose you want to assign a virtual address 800,000 exactly at the 8 megabyte address. And then like you want to map any kind of a physical page. So any free physical page, you can map any kind of free page, then you can use that. And then what we can do is we first need to check the page directory entry. A page directory itself is available. So before doing this, we need to allocate the page directory first. And then inside of the page directory, we need to check that the corresponding page directory. So PDE entry at 0 will manage from 0 to 4 megabyte. And then PDE entry 1 will manage 4 to 8 megabyte. And then PDE2 will manage an 8 to 12 megabyte range. So it will need to check the PDE entry 2 and then check if that entry is set with the PTP flag as 1. Then means the entry is available. Then you just need to follow the page table. Otherwise, that means like the corresponding page table is not existing at all. So we need to allocate that. So the diagram is somewhat wrong. So the actual link should be at the PDE2 because the memory address is at the 8 megabyte. Yeah, but please regard this as at the PDE2. I will change the slide accordingly to not making any confusion when you solve the quiz. Yeah. And then suppose the entry was empty. then what we need to do is we need to get a free physical page to allocate a new page table. And then suppose that new page address is 11223.0.0.0. So this is also page aligned because we just get a one free page and then use that as a page table. And we need to link this new page table to the corresponding entry. So we need to put the physical page number, just removing the last 3 zeros, and then put that on the page directory entry. So there are flags here, but that is omitted. But you can regard that like it's just purpose of the demonstrating how we can link the page directory and table with the physical address. So the logic is that if the page directory entry is empty, that means page table is not existing. So we need to allocate the new page table. So just get a new free physical page and then assign that into the page directory entry. And then now we have a page table, and then the new page table do not have any kind of entry. So after following, so if we get the top 20 bits and then get the last, the middle 10 bits, so it'll be 0. So that's why we are referring to the PT0. And then because it's empty, we can check that emptiness by checking the PTP flag on here. But assuming that free physical pages are like wiped as all the contents are 0, then these are all naturally invalid. And then right now you want to allocate a real physical page for this virtual address. And to do that, you can get another free physical page. So that will be really used for backing this virtual address, and then get that, and then put the physical page number at here. So that's it. So there's no relation between the physical page number of the page table, page directory, or the actual physical page backing the virtual address. So all these are all independent physical pages. And then we are creating a data structure starting from the CR3 register that we can follow the translation with the page directory and table. So any questions up to this point? Yes? So we will have one page directory per each process. So how it works is like the operating system in the memory, it will store, so you can think it as like there's a process object. And then process object has a member variables. So it will store all the CPU register state. And then inside there's a CR3 register value. And then that points to the page directory. And then at the process creation, you also need to create the page directory because that's actually giving the virtual memory space to the process. And then if we go one step more, think about thread. Thread in Linux is actually the different process, but you can regard that as like a different process that has the same CR3 value. So that it will share the page directory, so it will have the exactly same page table. Go ahead. All right, then let me move on to the next part. Yeah, so we learned about that to assign a physical, to map a virtual address to a physical address, we need to check the page directory first. And if it exists, then we just follow to the table. But if it does not exist, then we need to allocate a new physical page to allocate the page directory, and the new physical page to allocate the page table. And also we need to get a new physical page to actually backing the virtual address. Then the question is that we need to keep track of all the free physical pages on the system. That's the job of the operating system. So I believe you have experience with the using analog and free to manage your own heap memory in C in CS344. So if you do not use the free function correctly, then you will allocate a lot of memory, and then it will stay there even if you don't use that. So that kind of the memory leak problem is there. So the same problem could happen in the operating system side. So like this kind of the managing how much of the free physical pages are there. Yeah, these are very important to the operating system reliability and performance. So so not the exact reason for much for these days, but in the era of using Windows 95 and 98 or something, yeah. So if we use computers for 20 hours or something, then the computers get slowed down. So the main reason is like that was like the operating system cannot catch this kind of the memory leak problem correctly. So that there was a problem in managing the physical memory pages. But in these days, there is no like that kind of the weird error in the operating systems. So how JOS manages the free physical pages? So to do that, we use a special structure called the struct page info. And then I will show you the struct page info, the source code first. So the struct page info is that it has a pointer. So there's a pointer, and then this pointer is just for creating a linked list. So you can think it as there's an object, and then at the end, it has a link, and then it will point to the next free physical page. And then we will manage free physical pages as a linked list. And then there's another variable, ppref. And then this ppref is reference counter. And then we will set this as 0 for the free physical memory pages, and then non-zero for the pages that are in use. And then whenever we increase the use of the physical page, for example, we map a virtual address to a physical address. And then please think it as like the virtual to physical mapping is n-to-1 mapping. So for one physical page, we could theoretically have n number of mapping virtual pages. So this ppref could be big. For example, 1,000, 2,000 or something like that. But the reason why we keep this kind of the reference number is that like we would like to know the exact timing that all the address translation was delinked. Then like we can catch that moment by checking the ppref value as 0. And then you are required to manage this number and the linked list correctly for lab 2. So we will have that kind of struct page info, and then this is just an 8-byte structure. So let me explain why it is an 8-byte structure. So we are in the 32-bit machine, and the pointer. So all the pointers are 32 bits. So this to store the link address. So it requires a 32 bit, 4 bytes, and then another type, the reference counter, was like the uint 16t, so which is 16-bit integer. So that's actually 2 bytes. Then 4 byte and 2 byte, 6 byte. But why do compiler generates this structure as an 8 byte? The reason is like if the memory is aligned with the 8, 16, 32, so that kind of multiplier, then like the CPU will read the data a little faster. So there is like some of the hardware limitation that like for the unaligned memory. So sometimes we need to read 2 blocks and then take 1, because memory data is like reside across some of the boundary of the memory block that they can read from the hardware. So the general practice for the compiler is that to generate the aligned, so aligned to 4 byte or 8 byte, 16 byte, so that kind of the size to that kind of size, generating that kind of structure will make the program a little faster. And then how we will use this struct page info is that we will create this 8-byte structure for every single physical page. And to be specific, in JOS with the default setting, our QEMU will run with the 128 megabyte of the physical memory. So 128 megabyte, and then, so we want to count the number of pages, total number of pages, and then page size is 4,096. So that's actually 32,768. So actually it's 2 to the 15. Yeah. So that's the number. And then we need that number of a page info struct. So each is 8 byte. So by just spending 256 kilobyte, we can manage 128 megabyte. So it's quite small and efficient. So we just use like this kind of naive structure for managing the free physical pages. And then we will use it as a linked list for free one. And then I will show you how we can build that. And then I will also describe how we will use ppwrap. So there is a global variable called the struct page info pointer pages. So please do not regard this as a linked list or something. So this pages is just an array. So let's blame the C language. So the C language it has a type for the array, but it does not have like the strict distinction between the array and pointer if it is in one dimension. So we can use this kind of the pointer type for array and also for the real pointer to create a linked list or a tree. But you can regard the struct page info pages, this global variable, as an array. So what we will do is in this variable, we will allocate in a contiguous space in the virtual space, we will allocate the entire structure for the physical pages. So we just calculated if suppose there's a 128 megabyte of the physical memory is available for JOS provided by QEMU, then we will have 32,768 pages. So we will basically create 32K entries. So exactly this number of entries of the struct page info. And then we will use the ppwrap to store the reference counter. So at the start, you can set all the reference counter as 0. That means all the pages are free. And then we would like to link free pages as a linked list. So this is an array, but you can link the free pages as a linked list by using the pp-link pointer like this. And then you might be curious that how we can map a physical page to the structure of the page info. And then we don't have any programmatic link between the physical page and this structure. So ppwrap is just a 0, 1, 2, 3, that kind of value. And then pp-link points to another struct page info, so free pages. Then how we can, so the exact question is that, suppose you are playing with the page info at index 3. Then which physical page will be the corresponding physical page? So there's no information about the address of the corresponding physical page, but you don't have to worry because we create this array with the total number of the available pages so that each one can be directly mapped to the physical pages. So for the page info entry, index 3, that will manage page 3. So the page info index 32K at the end, so that will manage the last page. So we will take a look at this more detail in the latter part of this lecture. So the important thing is that we create the same number of the struct page info for the all available physical pages. And then we marked all the ppwrap as 0. And then at the start, there's no link. And then we need to mark some of the pages that are in use when we set up the virtual memory. So what that means is that right now, we loaded some of the code in here for the bootloader, and then we also loaded the kernel, and then we also need to allocate these kind of the page info structure. Then we have already used some amount of the memory, and then we need to exclude them from the free physical pages. Then we can manage the free memories correctly. Otherwise, like we can allocate some of the physical page that is used by kernel to the user level program, then that could be a disaster because some of the changes that user made will be shown on the kernel side. So to get the free memories, so we have some of the steps that to take to mark all the in-use memory correctly. And then first thing is that we need to point where the kernel code ends. So to that end, we can refer to the boot alloc function. So the boot alloc function, we will use that for allocating the physical memory. So we will not use this function after we set up the virtual memory. So in lab 2, you will be mainly playing with this boot alloc function to allocate the physical memory. And let's take a look at the code. So there is a static character pointer next free. So you can regard this static keyword as creating a global variable that can only be accessible inside this function. So nowhere else you can access next free. You can only access next free inside of this boot alloc, but if you make changes to the variable, then that will be persistent for the subsequent function call. And then what it does is that, so external character end. So there is a symbol that we have created for JOS that you can access where's the end of the kernel code from the C language. So there's a symbol end. So you can refer to that variable to point to the end of the kernel address. So we know that our kernel is loaded exactly 1 megabyte of address because we did that when we load the kernel in boot.c in the bootloader. Yeah. And then the end will be somewhere above that address because kernel will take place as some part of the memory. And then how we set the first next free is, so we want to be a page aligned because we will manage physical page as a page granularity. So we round up the end address to the page size. So if it is exactly at the page boundary, then we don't have to add anything. But if it is like the 1 byte over the page boundary, then we need to add 4095 to make it as a 2-page, something like that. So after doing this, what next free for the first initialized value will point to not exactly the end. So it'll be a little above the end, but it will contain the entire kernel region. So, and then we can regard after loading the kernel. So because the kernel end is here, and then our first call to next boot alloc 0 will return this address. So you can regard anything after next free is free. And then we need to allocate struct page info for the 32,000 physical pages. And then to do that, so we need to allocate the pages array. And then how we can do that is like after implementing boot alloc correctly. So we can specify the size of the physical memory to allocate in the boot alloc. And then what we will do is the variable end pages. So it stores the total memory divided by the page size. So it will store the total number of the physical page and then multiplied by the size of our struct page info. So this is actually 8. So it will allocate 256 kilobyte for this kind of structure. And then that will move our next free up to here. So you can regard the next free variable inside the bool lock. What it does is like it will at the start, it will point to the end of the kernel. And then if you allocate 3 pages or something, then it will go up 3 more pages. And then 256, that's actually 64 pages. So it will go up for 64 pages for the next free after calling the bool lock. So the correct behavior of the bool lock is that so you will return the previous next free as a memory location, but you need to update the next free to the by adding the allocated size, round up with the page size to correctly mark where is the next free. And after doing this, you know that starting from 1 megabyte, and then if you call boot allot 0, then it will just return next free. Then from 1 megabyte to the next free, so these are occupied. And then you can regard from next free to the end, that will be free physical memory. And then there are something we need to take care about, the lower part of the memory. And then when you get to the page init function, then there is a description about like how you need to manage free physical memory for the low memories. So the first is that you need to mark physical page 0 as in use. So it's something like this. You need to mark page 0 as in use. And then can you guess why do we need to mark physical page 0 as in use and then we should never use that? So, yes?
Maybe it is storing the resistance
not exactly. So the similar mechanism is implemented in malloc. So if you call malloc in Linux or any other operating system in default setting, it will never return address 0. So in Linux, there's a configuration option that like you can set what is the minimum address returned via malloc. So that's actually 64 kilobyte. Then can you guess why do we have that kind of setup? So the important point is that the operating system will never return address 0 as a valid address. Yes? That's right. Yeah. So in general practice of the C coding, so we use a lot of the null keyword to specify that the object is not existing. So the null is 0 in C. So we don't have like a non or that kind of type in C. So we use null 0, actually 0 value as the non-object kind of the semantic. Then if we allocate address 0 as a valid address, then we cannot distinguish whether that is a valid object or like null object. So like we don't use the address 0. So that's the reason. So that's the only reason for making the page 0 as a not accessible. And then the rest of the base memory. So the base memory means that the memory below the 64 kilobyte, and then you can point that with the IO physmem then as an address. So that actually, that is exactly at the point where the base memory ends. So you can mark page 0 as in use, and then from IO physmem to external physmem, so this region, so we use that for controlling some of the basic devices. So it's something like a video graphic adapter, and then some other peripheral hardwares, keyboard, mouse, that kind of thing. So we need to reserve this memory. So you need to make this range as in use. That means that you need to set the corresponding physical page struct info, their PP rep as 1. And then the final description is that some other memory over the external physmem has already been occupied. So that's actually the kernel and the struct page info that we have allocated. So how you can mark the physical pages that are in use in this page init function is that, so just follow this diagram. So mark page 0 as in use. That means pages array indexing 0. So that's actually the struct page info for the physical page number 0. So that is in use. So you need to set its ppref as a 1. And then from the pages from here to here and more. So how you can do that is like starting from IO physmem to the next free. So you can get the next free as a Buddha log 0. You can mark all those physical pages as in use. So like that, I created a slide for this. So if you want to point next free, so where is the up to where we have used the physical memory. So that's the pointed by the next free. And then to point that, you can calculate something, but that's actually done by the Buddha log function. That's why we have a global variable next free in there. So just call this, then you can get the next free. So starting from IO physmem to next free, you can mark all pages as in use. Any questions up to this point? All right, I will move forward. But there is one caveat when marking the physical pages as in use. So there is a section of the memory that we will call as a direct mapping. So the direct mapping address space is like the specified as starting from F0000000, so it's the top 256 megabyte of memory. And then we will use that region to map virtual memory to physical memory directly. So this is for accessing physical memory directly. So the reason is that suppose 100000, that address was physical, and then we turn on the virtual memory. And then after turning on the virtual memory by setting the CR0 register, and then right after that, CPU regard every address as a virtual. So before that, we need to create the physical, we need to create the page directory and table. So if you follow the JOS code correctly, then you have seen like all these kind of part. And then that means, so after turning on the paging, CPU will regard all the address as a physical, virtual address. So there is no way that we can access physical address directly. So that's why we create this kind of the direct mapping. So how we will use this address is that, so suppose we have an address F0001000. So that's actually pointing to the physical address 1000. So the translation is easy, just to remove the F at the first character. Then you can see the corresponding physical page of this virtual address region. And then for mapping this kind of the addresses, so these are not actually occupying the physical pages. So we are creating the direct mapping for the access method for the physical addresses after enabling virtual paging, virtual memory. So we need to map some of the addresses in this region. And then for that kind of thing, you don't need to mark the pages as in use. And then if you follow the code correctly, so the code will mention that for the bootmap region, so it should not change the ppref field because we will not manage reference counting for this kind of mapping. So please make sure that do not increase or decrease any kind of ppref inside of the bootmap region function. And then next is about the reference counting mechanism using ppref. And the method itself, the reference counting, is widely used technique in programming languages to catch the timing that the memory is not used at all by any kind of the objects. And then that kind of concept is not existing in C, but in C++, there's a template library called the shared pointer. So whenever you assign one pointer to another, then it will increment the reference. And then whenever the parent object got freed, then it will decrement the reference. And then at the time when the reference counting gets 0, then it will automatically free the memory. So in C++, if you use the shared pointer, then you could catch almost all of the memory allocation, deallocation errors. And then how we will do the mechanism is that we will use just a very naive mechanism to maintaining the reference counter. And then what we will do is we will count up the value whenever we assign a virtual address to a physical address. So whenever we map a virtual address to physical page, then we will increment the reference counter for that struct info by 1. And then whenever we deassign a virtual address from a physical address, so conceptually we are freeing the physical page. In that case, we will decrement the counter. And then internally, when we are decrementing the counter, when the variable gets the pp_ref value as a 0, then we will put that on the free linked list. So how you can set the struct page info for the reference counting is that for in-use physical page. So if you need to mark some of the pages in use in page init, then just set it as a pp_ref as a 1. Then it will be ignored from the initial free pages pool. So those pages would not be included from the start. And for not in use physical page, so we will keep this. So pp_ref value 0, that means the physical page is free. So we will keep this invariant for all free physical pages. And then for those pages having no reference, having no virtual address assigned, then we will put that on the pages free list. There's a global variable pages free list that manages all the physical pages, free physical pages as a linked list. And then we will create a link at the start, just including the pages with the pp_ref value 0. And then whenever we assign a virtual address to a physical address, then we need to increment the reference counter for the corresponding physical page. And then whenever we release it, we need to decrement the counter. And for the initial setup, you mostly need, in the page init, you mostly need setting the pp_ref as 1. So for pages in use like this, so you need to set the pp_ref value of those pages as 1. And then we will create the initial free physical pages after setting the sum of the in-use pages as a pp_ref 1. And how we will do that is we can create the linked list with the few lines of the code. So at start, page free list is just null. So we have no free pages at all. And then after setting the pp_ref for the in-use pages, so you just run the code so going over 0 to the total number of pages from the pages struct info array. So for the entries that has a pp_ref as 0. So pp_ref 1 means the pages are in use, 0 means that pages are free, and then put that as a list. And then these two lines are actually creating a linked list. So I visualize it a little bit. So you can think it as, so there's a pre-page as a free page. And then how you can set it as, you can set the link of the pre-page to be the page free list. And then set the page free list to point to the current page. So now we have a linked list like this. And then if there's another free page, then we will link the new page to the page free list, head of the list, and then make it as a head. Something like this. So if it iterates over the entire page struct info structure, then you will have the linked list of the all free pages. Any questions up to this point? Right. Then the next is about some small things. So there is a function called the page to PA. So page here means that if you see some of the variable or function name page, that refers to the struct page info in JOS. And PA here means that physical address. So what this function do is, if you supply the active object, active structure of the struct page info here, then it will translate that page info to the corresponding physical address. But the important thing here is that there's no physical address information in the struct. And how we can get the physical address, corresponding physical address is that, so it will just subtract pages from PP. So the PP is the current object. For example, as an example, we have the struct page info object at index 4 of the pages. And this operation, PP minus pages. So this exactly will return the current index of the object in the array, because pages is the array base. So from the item in the array, subtract the array pointer. So that's exactly returning the index of the array. And then we create the entries of the struct page info for the entire physical pages. So we have the same number, the total number of the physical pages of the struct page info here. And then how we will translate how we will link this entry to the real physical address is that we will just get the index of the object in this table. And then page shift here is like the 12. So it's actually multiplying 2 to the 12. So 4096, the page size. So that's how we calculate the physical page address corresponds to the specific page info. And then there is an inverse of that function. So if we supply the physical address, then PA to page. So it will return the corresponding struct page info object. And then to do that, so this is actually implemented in the following code. So what it does is, so pgnum macro, it will get the page number. So the getting the page number is easy, just to shift the address right for 12 bits. So it will remove 3 0 digits, the last 3 digits in the address, and then use that as an index from the table. Then if it is at address 1000, then it will return index 1. If that was 4000, then it will return index 4. So that's how we can find a corresponding struct info object from a physical address. Any questions about the page to PA and the PA to page and how they work? So I'm not sure how many of you have got confused about using the struct page info, because I'm teaching this class for 5th time, and then in every single offering, many of students asked about we have PP link, and then should we link a real physical page address in here? But that's not true. So that we will use PP link to just create the linked list. Then we will use PP ref for the reference counting. And we are not storing any kind of the physical page address in the structure. And then we will just directly mapping the index of the object to the physical page number. All right, this is the part that I prepared for today. And then for the next few slides, I will describe a little bit about the quiz. So there will be more detailed information about the quiz on the lecture video on Thursday, because I will give some of the sample questions, and also I will describe like how you get the answer in detail in the video. And the quiz will be open for 2 days. So I will open the quiz in the morning of the next Tuesday, October 18th. But I will open the quiz for the next day midnight. So the quiz will be ending on like the Wednesday, so Wednesday 11:59 p.m. Yeah, and then we will have no class for October 13th. So there will be a quiz prep video for that, and then on October 18th. We will have the quiz. So this quiz is online, so that you can take it wherever you can do, and then we will release on Canvas. So yeah, there are information, so they will be released on Canvas, so you can see from the quizzes menu. So that I will announce that when it starts, and then you can see the quiz 1 at the 8:30 a.m. of the Tuesday, but it will be ending on the next day midnight. And then I believe like most of the students can finish the quiz 1 in 30 minutes or 1 hour. So there will be 10 to 15 questions. I have not determined yet, but it's just a multiple choice questions. So you need to choose the answer. So, but I set it the quiz time as unlimited. So because there were some of the errors that your internet got disconnected or something like that. So I just want to make all of you guys free from that kind of hassle. And then I will give you up to 3 attempts, and I will take the best score. So one of the things that I recommend is that, so please take the quiz for the first time after studying something. And then suppose you got 11 out of 15, then means you got 4 wrong answers. So quiz will let you know which problem you got wrong answer. So try to print that as a PDF. Then on the next attempt, you will see that which answer was correct. Just choose that one. And then just focus on the wrong answers that you cannot get. This is the reason why I'm describing this is like there were some of the students who got 11 on the first trial, 13 on the second trial, but 7 on the third trial. So that actually happens. Yeah. And then begging me for having a one more chance. Yeah. Please do that on your side for that. Yeah. And then I will let you access any kind of material except for the internet or communicating with the others. So you can refer to any kind of contents from course website, slides, lab tutorials, and your code. And textbook is not required, but if you want to get more information about that, so I recommend referring to the textbook part that I excerpt from the book and then posted on the website. So the important thing is please do not communicate each other with the students during taking quiz. And then you can ask questions while taking the quiz, but TAs and myself will not reply if you are asking if this is a correct answer or something like that. So please ask the questions during taking the quiz if there is a factual error or if you cannot understand what's the question itself. There is one question.
Will it be taking our best attempt or only the last one?
So I will take the best one. Yes. So what I'm emphasizing is on the second or third trial, please get the higher score. Yeah. And then the quiz 1 will cover, there will be less than 15 questions, but I have not determined how many questions I will create. And then it will cover all 3 weeks of the material. So starting from the boot and protected mode and paging, virtual address, and then JOS Lab 1 and some part of the JOS Lab 2. So these are all will be included so that you can regard the things that we learned until today will all be included in quiz 1. And then like how I will create the quiz questions will be there will be a question, and then there are selections, and then I will paste some of the links that you can directly go and find some of the related materials for the question. So like what that means is like you don't have to search for which week it was for the slide or material. So like I will post a link to the which lecture slide will be helpful for solving the question. So you can regard the quiz as like your own self-studying time and to learn about the operating system in more detail. Any questions? All right, then like I will work hard to creating lots of like the funny quiz questions, and then like after you see my quiz prep video, then like there will be, I believe there will be no anxiety at all. Yeah. And then like have fun with the JOS project, and then have a nice day. Just to clarify.